Okay, let's continue with the Week 8 materials for building scalable distributed systems, which are focusing on scaling the data layer. And the topic of this talk is the thorny one of consistency in distributed databases. So there's two notions of consistency that we talk about in distributed systems, that of strong consistency and that of weak or eventual consistency. Strong consistency is the sort of consistency you're used to in business and financial systems, where all replicas of the same database object must always exhibit the same value to clients at exactly the same time. If you think about it in a banking application, if your data is replicated behind the scenes across different nodes and you query for your account, you expect to see the latest value for your bank account regardless of which replica is queried. If you see an old version and you've just deposited $1 million, then you're probably going to be worried. So strong consistency is the dominant form in finance and banking and government and many business systems. Eventually consistent systems allow some replicas to be out of sync and not up to date with the latest version for a particular database object. So this means that you may read from an out of date or stale replica, and eventually this replica will become consistent with the value of the actual object, the latest value, but it's not guaranteed to always be the same. So think about things like Twitter feeds or Facebook status updates. When you make an update or you post a new tweet, it's not the end of the world if all of your friends or followers don't see the latest version of your musings instantly. If some see them and some don't, you'll survive. They'll see them eventually. So let's start by looking at eventual consistency. The idea of eventual consistency is it promotes availability over consistency. So it means we can always serve a replica value regardless of whether it's actually the most recent value or not. So this is basically what's known as an optimistic version of consistency. And we can achieve consistency across all the replicas, albeit with some latency eventually, using background replication mechanisms across the replicas. So availability is achieved through replication and partitioning. Requires a successful write to one or more replicas, and then in the background the database will asynchronously, typically asynchronously anyway, send the new value of the database object to the other replicas, which will eventually commit this so that all of the values are consistent. And the latency, of course, for achieving consistency is affected by the number of replicas. If there's a 1 replica, updating this will be much quicker than probably updating 7 replicas. So let's just have an example of how this works. Here we have a database object with the value of 1, which is replicated 3 times across 3 different replicas. And we have client 1 and client 2. Client 1 makes an update, sends a new value for this particular database object, a value of 5, and it happens to be sent to replica 2. Replica 2 now becomes the node which is responsible for sending the new value to the other replicas. So it persists the value locally, sends 5 to replica 3, which says thank you, I'll update my value, sends 5 to replica 1, which says thank you, I'll update my value. And in between this update and this update, then the value was inconsistent, but it got there eventually, which is all that matters in this particular case, because when client 2 comes along and it reads from replica 1, it sees the value of 5, which is exactly what we want. So just to summarize, client writes are sent to a coordinating replica. The coordinating replica is responsible for updating locally and informing the client that the update is persisted. It then sends the update to the other replicas and waits for an acknowledgement. If a replica isn't available, then things get tricky, and we'll come back to this a little bit later when we discuss something called hinted handoffs or sloppy quorums. But if there's n replicas, and clients may choose to write to greater than 1 replica. So a client may say, I actually want to write to 2 of 3 replicas to make sure that there's less chance of a client getting an inconsistent read, because 2 of the replicas will be correct, and then the chances of it seeing the third replica are less. But this, of course, will increase your write latencies. So decreasing the inconsistency window is good. Longer write latencies, not so good. Another example. So here we have client 1, again writes the value of 5 to replica 2. It persists it and now coordinates the update to the other replicas. Sends the value to replica 3. It sends the value to replica 1 at pretty much the same time. But replica 1's busy. Maybe it's got a blast of requests from a million clients, or maybe there's a slow network or a transient network failure, and it doesn't receive, or it doesn't have a chance to persist the new value before a new client comes along, issues a read on the same database key, and this read is sent to replica 1. It's a masterless, a leaderless system, and hence replica 1 is the leader for this particular request. It's not seen the new value yet, so the client reads the value of 1, which is stale. It's actually been updated, but because we're reading from a non-updated replica, we see the old value. 5 eventually gets written, but we've basically seen a stale read. So this is one of the consequences of eventual consistency. In many applications, it's necessary for clients to read their own writes. A really good example of this is changing the default credit card on a system such as Amazon or eBay. So your credit card's expired, you've got your cart full of gear that you want to buy, you go to checkout and the site says, you need to change your credit card. So you say, okay, here's my new one, you store it, you hit submit, it gets validated, and then you go, great, I'll try checking out again. Now you can imagine in the background your credit card is replicated across multiple nodes, and it's updated on some nodes and not on others. So when you now go to check out again, the read for your credit card details gets sent to one of the replicas which has not seen the new credit card value. So we read the old credit card, which is not good, because in this particular scenario you would always expect to read the new credit card value, and hence you would expect to read your own writes. Let's look at how this might work. Again, here we just have client 1, same value spread across 3 replicas. We make an update to replica 2 with the value 5, gets coordinated to replica 3, it also gets coordinated to replica 1, but as in the last example, replica 1 is super busy, and client 1 now reads its credit card value based on the previous example, but the read is coordinated by replica 1, which has not seen the new value, and I get the old value, so I'm not reading my own writes. This, in many application scenarios, is not a good thing. One way to coordinate reads and writes across replicas in a distributed database is to use the notion of quorums, or majorities. So in a leaderless system, let's define the values of n, w, and r, where n is the number of replicas, W is the number of replicas that need to be updated on every given write. Of course, W is less than N, and so similarly, R is the number of replicas that need to be read to get the latest value. So for this system to work, we need to assume that data is somehow versioned with a version number or a timestamp, so that the database can discern the latest value for a particular database object. Let's have a look at how this might work. Back to our example, 2 clients, and in this system we need to write to 2 replicas before a write is considered successful, and we need to read from 2 replicas to try and get the latest value. So once again, we write the new value of 5 to replica 2, it gets persisted. We coordinate that value to replica 3, again it gets persisted. And client 2 now has a R value of 2 for this particular read, which is sent as usual to replica 1, which has not received the latest value. The write hasn't fully propagated to replica 1, so it's still got the old value. But because we're reading with an R value of 2, replica 1 will say, okay, I've got a value, I'm going to get a value from another replica. So it goes to replica 2 and says, what's your latest value for this request, this database object? And it says 5. And now because the database can discern the latest value using a timestamp or a version, replica 1 says, oh, I'm out of date, there's a later version. So I'm going to return 5 to my client so it gets the latest version. And of course, eventually, replica 1 will get updated to the latest value. So that's how the W and R values can help us get rid of stale reads. So quorums are useful. The basic rules is if W and R obey the n over 2 plus 1, then this is known as a quorum. It's essentially a majority. So if n is 5, W needs to be 3 and R is 3. Or W plus R need to be greater than n. Will we get read your own rights using quorums? Well, if everything works fine, yes, because there's an overlap in the set of nodes that are written to and read from. But as you know, in distributed systems, not everything works fine all of the time. So 2 scenarios where quorums may not give us the desired outcomes. First one, a write is in progress on a particular database object when a read is issued on the same one. So the write may have a value of W equals 2, but the new value has not been fully persisted in all the replicas. So in our previous example, we may have only persisted the new value of 5 to one of the replicas. The read comes along before the value has been propagated to others. The read value is 2, but it goes to the 2 replicas which have not been updated. Or it goes to one of the replicas which has and one that hasn't. We don't know what's going to be returned. So that's definitely a risk that would not solve your read your own rights problem. And also a write may succeed on some replicas but fail on others because it's maybe not accessible due to a network partition or the node is actually down. And so we can't achieve the W value for the replica updates. What do? Well, you don't roll back writes in this situation. That's too much overhead within the database system. So we could return an error to the client, which could retry the update. But if there's no retry, then reads may return stale data because the object is not consistent across all replicas because one's not available. There's a solution to this. It's known as sloppy quorums or hinted handoffs, and let's talk about those soon. One of the powerful things about quorums is we can adjust the values of R and W to give us some desired qualities for our system in terms of performance and scalability. So let's think about the first example. All of these have an n value of 5, so there's n replicas for every database object. If we set the W value to 1 and R to 5, what's the effect here? Well, it means when we do a write, we only have to update one replica before the write returns. So this will create fast writes. But when we do a read, we have to read all 5 replicas to get the latest value. Now this will work. It will give us the latest value even though only one has been written to, even if the other replicas are not updated, because we're reading all replicas. So what we're achieving with these values are we're getting very fast writes, we're getting slow reads, but we're always getting the latest value. We can turn this situation around. We say we only need to read from one replica, but we know we're going to get the latest value because we're going to write to all 5 every time we write. And so this will give us slow writes, but fast reads. In this particular scenario, we only write to one replica before the write succeeds, and we're reading from 2. So there's no guarantee that any write will have been propagated to the 2 replicas that we're reading from here. So this one can give us stale reads, but it's going to give us fast writes and pretty fast reads. So you can adjust these values to suit the performance and scalability qualities that your system desires. Now, as we mentioned, it may not always be possible to achieve the quorum settings for a write. In the case of perhaps a network partition, the client writes or reads cannot achieve the necessary quorum. In the case of a write, if a write is made to a coordinating node but it can't see other nodes, say and the W value is 2, what's it going to do? It can't satisfy the request to write to 2 replicas. So what we can do is use something known as a sloppy quorum. And instead of writing to the node where the replicas are stored permanently, we can make the write durable on any other node we can access. And this becomes a temporary home for the actual value. When the real replica comes back that hosts that particular value, we have something called a hinted handoff occurs, where the replica value is updated based on the value that's stored in this temporary home. So you can see here, client 1 writes the value of 5 to replica 1, but it can't see replica 2. The value of W is 2, so it can't achieve the W setting that's desired because it can't see replicas 2 and 3. So it writes the new value locally and to any old node it can find in the system. This is the temporary home, which when the network partition is healed, this will notice that this has a value for some replicas which are now available, and the 5 will propagate through to become the value of the object. So quorums really help us control consistency and how long the inconsistency window is open for particular reads and writes. But there's one problem they can't solve, and that's one of conflicts. And a conflict occurs when writes to the same database key occur at different replicas at the same time. So basically overlapping writes. 2 clients make an update to the same database object, but one is sent to one replica and one is sent to be coordinated by another. And so essentially what this means is the writes don't know about each other. The 2 coordinating replicas for the particular write have no idea that the other write is occurring at essentially the same time. And this creates problems with the way we handle replicas and updates. Let's see how this works. So again, we have our normal situation, 3 replicas, value of 1 for a particular database object, and 2 clients. Client 1 writes the value of 5 to replica 1, and at essentially the same time, maybe slightly after, client 2 writes the value of 7 to replica 1. So replica 2 sees the update, updates locally. Replica 1 sees the update and also updates locally. These are now the coordinating replicas for these 2 requests, and their job is to make sure that the other replicas have the same value. So replica 2 does its job. It writes the value of 5 to replica 3, which is great. And then the next thing that occurs is replica 1 sends the value of 7 to replica 3. It updates its value and 7 is now persisted, which is good because we're assuming that the update for the value 7 occurred very slightly after the update for value of 5. So 7 is probably the value that we need. And then replica 2 says, okay, I need to update replica 1. Here's the value of 5. And at the same time, or maybe slightly after, replica 1 says to replica 2, hey, I've got a new value for you, here's 7. Replica 2 stores the new value 7, which is good, that's what we want probably. But replica 1 gets a new value of 5. So we have inconsistency. This overlapping write has caused a conflict. We have 2 values with 2 nodes with the value 7 and 1 with the value 5. So this is not good. And one solution to this particular problem is to use an algorithm called last writer wins. And last writer wins assumes that updates are associated with a timestamp. and we can compare timestamps to determine which is the most up-to-date value for a particular database object. So if we see conflicting writes, we simply persist the most recent value by comparing the timestamps. And this means that all replicas will have the value of the value associated with the latest timestamp. And it ensures they remain consistent. But the problem is, as you hopefully all remember from a previous session in this course, time is a tricky beast in distributed systems. So if we're comparing timestamps, which clock generates the timestamp? Is it the different clients that are sending the updates? Well, they're probably not going to be the same. What about the coordinators? We've got different nodes coordinating the updates. Their clocks might not be the same either. Or the replicas themselves, well, if there's 5 replicas, they're unlikely to have the same timestamps either. So this is a real tricky problem, and let's illustrate it here. We have a playlist which is empty. Client 1, a Rolling Stones aficionado, adds the song Angie to their playlist. Their playlist is shared with another client. Maybe it's me and my wife sharing a playlist, but it wouldn't be the Rolling Stones. And client 2 reads the current status of the playlist. And client 1 eventually says, I'm going to add some more songs to this playlist. It's not very long. So it reads the current value. So both client 1 and client 2 now have read the current value of the playlist. Client 1 comes along and says, let's add Brown Sugar, real funky song. I love that, adding that to my playlist with Angie. And client 2 says, I think I'll deliberate for a bit, but I'm going to add Paint It Black and write this back as the latest value of the playlist. Now, last rider wins. This is the most current value. So it should be written as the value for this database key, for this playlist. But what happened to Brown Sugar? Client 1's pissed because their update to the playlist has disappeared. So we've lost an update. And this is what happens with last writer wins. So last writer wins is effectively lose some writes. It's effectively a race condition. Writes can be overwritten and they're reported to the client as successful, but you can lose values that were written by other clients. So last writer wins inevitably leads to data loss. And when it's the mechanism which is used to handle conflicts, the only time it is safe is when a key, any particular key, is only written once and is always regarded as immutable afterwards. If you want to make updates to that particular key, you don't update the actual record itself, you write the changes to new rows in the database, and then somehow, probably in the application, you merge the updates with the original value to create another row. So writes, new values once written to the database are immutable, and it's the only way you cannot lose data with last writer wins. This is a problem which is well known from databases like Cassandra, which do use last writer wins to solve conflicts on overlapping updates. And if you don't use Cassandra as essentially an immutable data store, then this will occur. So we can't use timestamps to solve conflicts. There's one solution we can use though, and that's based on the notion of causality. So let's look at what this means through an example here. We have 2 users who have to log into their systems at 8 AM. Maybe that's the time they're expected to be working on their call center, for example. Now we know that 8 AM on one user's machine is unlikely to be exactly the same time as 8 AM on another user's machine because clocks drift. So how do we know which one logged in first? Let's assume user 1 logs in, and as soon as a user logs in, it sends a message to user 2 saying, I've logged in. And that message is received before user 1 logs in. In that case, we know for certain that the user 1 login happened before the user 2 login, because it received a message saying that user 1 had logged in before the user 2 event occurred locally. If the message is received after user 2 logs in, what do we know? Well, not much, unfortunately. We don't know the order because user 1 may have logged in before user 2, but by the time the message was sent and received, while the message is in transit, for example, user 2 logs in. And there's no way we can discern which events happened before the other. So in this case, we regard the events as concurrent. They happened at the same time and we can't establish causality. The basic approach to establishing causality was devised by Leslie Lamport and is called Lamport clocks. It's a simple algorithm that can be used to establish a partial ordering of events in a distributed system. Essentially, every process maintains a logical clock, which is a counter. It starts at 0 when the process starts. When the process sends a message or executes some internal step that it wants to be able to establish a causal relationship between, it adds 1 to its clock. If the process sends a message to another process, it piggybacks, or it adds its local value to the message. And when a process receives a message, it sets its local clock value to the maximum of its existing clock value and the one sent in the timestamp, and it adds 1 to the value because it's a new event, and we always increment the clock when a new event occurs. And the resulting clock is taken as the time of the receipt of the message. So how does this look? It's an example from Wikipedia. We have 3 processes, P1, P2, P3, and in process 1, event A occurs and we increment our clock to the value of 1. The clock starts at 0 in all of these. And then event B occurs and we increment our clock to value 2, and we decide to send a message to process 2. Process 2 receives the message, says, okay, what's my local clock value? Well, I've not done anything, so it must be 0. I'm sent the value 2, so I'm now going to set my local clock value to 2 plus 1, which is 3. Then soon after, event D occurs, which requires process 2 to send a message to process 3. It increments its local clock, so it knows that 4 is greater than 3, so C must have happened before D, and it sends the message with the value 4. Process 3 receives this, and its current clock value is just 1 because it's just done one event E, which was of note. And so it says, okay, I've received 4, mine's 1, so the new clock value is going to be 5. So what can we establish from this? Well, we know 1 is less than 2, so A happened before B within that process. We know that C results from has a clock value of 3, so we know that C happened after B, or B happened before C. In the same process, we know C happened before D, and we know that D happened before F, because we can compare the clock values. What about here? What about E? What can we establish about E? Well, we know E happened before F. What about A or B? Well, we have no idea because there's no causal relationship between these. These counters are in different processes and they just were incremented independently. So these events are concurrent. We can't establish any relationship between those particular events, or these particular events either. So Lamport clocks establish a partial ordering of events amongst the processes in a distributed system. So it establishes the happen before relationship, whereas if the clock for A is less than the clock for B, CA happens before CB. And it's only meaningful in terms of the group of processes which are exchanging messages. So this means that Lamport clocks only work in a closed group of processes which exchange messages. So with this kind of mechanism, how do we handle conflicts? Well, let's look at an example again using our good old playlist. Client 1 writes a new value to the playlist, good old Angie. Client 2 reads the current value of the playlist, starts playing Angie, and client 1 does the same, reads the current value and starts looking at what else to add to the playlist. It decides to add brown sugar and writes this back as the value associated with the key playlist. Client 2 then decides to write its new value for the playlist with the song Paint It Black and Angie. Now here, with our old scheme, this is a conflict and we would lose this update. But if we want to handle conflicts, the database would say, hang on, this is an update to a key which has been updated since client 2 read the value. So what we can do is say, these are what is known as siblings. It's a conflict occurred, and someone has to merge the value of the two updates to create a consistent entry for this key. And if we do that in this example, we would basically merge the contents of the last two updates, so the playlist now has 3 songs instead of 2. So how do we detect these conflicts? Lamport clocks can't do that because they can't detect concurrent events. So what we need to do is have some form of versioning, and there's 2 approaches to this. They're similar in nature, vector clocks or version vectors, and they're both based on the basic mechanism of Lamport clocks. And basically they associate a version number with a particular database key and value, and when the value changes for that particular key, the version number is incremented. When 2 clients read the same version and make updates, then the conflict can be detected, and the database can say, I have 2 versions of the same database key, which are known as siblings, as we saw on the previous slide, and it can tell the client that this needs to be resolved. So it returns the value of the 2 conflicting updates to the client and says, you fix it. And it can either be done algorithmically, or maybe you need a person to help fix the conflict. Some databases also have data types known as conflict-free replicated data types. These are sets, lists, basic data types that you're used to in languages like Java. And when conflicting updates occur to database objects which are based on these structures, the database itself can resolve the conflicts using well-known algorithms. So this is the basic approach. We read the value for the playlist, and the version vector or vector clock, the version is 1, and client 1 reads the value and gets passed the current version along with the read. It then writes back the updated value, and it presents along with that write the version of the object that it read. So it read version 1 and it's updating version 1. The database says this is cool. This means that the database has not changed since this client read the value, so we'll create a new version and allow the update to happen. Client 2 comes along, it reads the playlist value, and because this is a new version, it gets the new version value, the new version vector or the vector clock, number 2 in this case. And client 1 comes back and reads the same value, and it gets exactly the same version. So now we have both clients have read the same version of the playlist. Client 1 comes back, makes the update first, presents the version value that it read. The database says, it's not changed, this is good, I'll accept the update and increment the version value. Client 2 comes along, it writes its update along with the version value that it read when it read this value, and the database says, hang on a minute, that's version 2, but we're now version 3 in the database. So this is a conflicting write. We have siblings, and I'm going to try and force this client to merge these updates. So it returns from the write, it returns a new value of the version vector, and it returns both siblings. So the client 2 needs to figure out how to resolve the siblings to merge the values, and it writes this back with the new version of the version vector that it read here, and the database says, oh yeah, this is now merged, we're good. We've fixed this conflict. So the basic idea is that for conflict resolution, the server creates a version for each key replica. Clients read the key and get the associated version before writing. When they write back, they also present the version that they read. If the version of the database object is exactly the same as the one associated with the write, the server updates the value and creates a new version. If the server version is not the same, the server creates siblings, and it asks the client to resolve the updates, the conflicting updates, and writes, and once that conflict is solved, it creates a new version value. Next week, we're going to talk about strong consistency and the several forms that it takes in distributed database systems. So in summary, relational databases scale best when you scale them up, and they're suited due to the nature of the relational model and SQL to business data, which is strongly consistent. Different application types such as social media or sensor-based data can tolerate weaker guarantees of consistency, and by tolerating this they can scale wonderfully. NoSQL databases are based on different data models and query languages, and they're typically replicated using either a leader-follower or a leaderless system. Mostly they implement eventual consistency, and you can achieve this in leaderless systems using quorums. In such systems you also get conflicting writes, and to resolve these you need some form of versioning system such as version vectors or vector clocks to handle conflicting updates in distributed systems.